Now let's shift from credit risk to operational risk, and specifically to fraud detection, one of the most high-impact applications of AI in risk management. So banks, healthcare services, education establishments, manufacturing firms, and government agencies can all leverage AI to monitor financial transactions. The scale is huge. A major bank might process millions of transactions daily, which makes manual review impossible. In operational risk, fraud is one of the major areas where AI creates enormous value. Fraud detection by traditional methods is incredibly labor intensive. Someone has to notice something odd, investigate it, trace the money, interview people, and so on. By the time you catch a fraud, substantial damage may have already occurred. But here's what AI enables. Using algorithms trained with historical data, banks can now suggest in real time which transactions are suspicious. These might be suspicious logins from unusual locations, identity theft attempts, or fraudulent transactions. The system flags them instantly, often before the transaction even completes. This is huge. Instead of discovering fraud after the fact, organizations can prevent it or stop it within seconds. The speed advantage is enormous. Okay, so we've spent time exploring the business applications and value of AI in risk management. Now let's shift gears and develop a deeper understanding of what AI actually is and how it works. So artificial intelligence is a term that most people in the modern world are familiar with, especially after the recent explosion of AI in the news and in popular culture. But let's be precise about what it means in a technical sense. AI, as the name implies, is intelligence that can be programmed or constructed artificially. That is built into a computer system through software and algorithms. It's not biological intelligence like human intelligence. It's intelligence created by humans, embedded in machines. How is this intelligence created? AI is programmed by feeding a computer system a large data set and training it to recognize patterns in that data. So the system then uses those learned patterns to respond to questions about the data accurately and intelligently. So for example, imagine you want to build an AI system that can recognize whether an email is spam or not. So you would start by feeding it thousands of emails. Some are classified as spam, some are marked as not spam. The system then learns to recognize patterns that distinguish spam from non-spam emails, certain word combinations, for example, or sender characteristics or structure elements, and so on. Once the model is trained, then a new email arrives. The system applies these learned patterns and then classifies that new email as spam or not. So the intelligence is not pre-programmed as a set of explicit rules. So the intelligence is not pre-programmed as a set of explicit rules, like, for example, if the email contains a word Viagra, mark it as spam. But instead, the system discovers the patterns from the data itself. So this brings us to machine learning, which is crucial to understand because it's the mechanism that powers modern AI. So machine learning is a process within the broader field of AI. More specifically, it's a discipline of AI that provides machines with the ability to automatically learn from data and past experiences while identifying patterns to make predictions with minimal human intervention. So notice the key phrase here, minimal human intervention. So this is what differentiates machine learning from traditional programming. In traditional programming, a human explicitly tells the computer what to do. If X, then Y. In machine learning, the human sets up a framework and process, feeds in data, and the system figures out the patterns and rules on its own. The data feeding and training process we discussed, which is done through a mechanism called machine learning, and machine learning is the engine that powers AI. So there are multiple approaches and techniques to machine learning, and they're used for different purposes. So this slide shows us different key components. So first we have deep learning, which uses neural network with many layers to discover complex patterns in data. This is particularly powerful for images, audio, and text data. Then we have algorithms, which is the mathematical procedure and processes that the machine uses to learn. So we have different algorithms that are suited to different problems. And then you have learning, which is the core process where the system improves based on data. You have improves here, which means machine learning systems get better over time as they see more data and refine their understanding of the patterns. There's analyze. The system can examine data and extract insights, of course. Autonomous systems. So machine learning enables systems that can operate independently, making decisions without constant human guidance. We have classification, which is organizing data into different categories. We also have data mining, which is discovering patterns in large data sets. And finally, we have neural networks, which is computational structures inspired by biological brain, and they're excellent at finding complex patterns, especially in nonlinear and unstructured data. All of these components are interconnected. They work together as part of the broader machine learning ecosystems. Now, let me explain machine learning more formally. So machine learning is an application of AI that allows the system to train, learn, and improve based on experience rather than being explicitly instructed to do so. This is fundamentally different from traditional programming. So here's how it works. The machine is taught to look for specific aspects of a data set, then provide inferences like conclusions or predictions based on what it has gathered. It's looking for patterns, relationships, anomalies, and structure in the data. Over time, the machine will use this data and a set of algorithms to imitate the way that humans learn. When you learn something new, you integrate it with what you already know, refine your understanding, and apply it to a new situation. Machine learning does something similar. It processes data through algorithms, updates its internal model of how the world works, and gradually improves its accuracy at making predictions or decisions. So the key insight is this gradual improvement in accuracy. The machine learning system doesn't become perfect immediately. It starts with limited accuracy and improves as it sees more data and gets feedback about whether its predictions were correct. So let's look at the machine learning workflow. The actual workflow of machine learning is similar to what you're seeing in this slide here. And this is how actually it works in practice. So it starts with training data, which is typically historical data that we use to teach the system. So for example, in our fraud detection scenario, this would be thousands of historical transactions, some labeled as fraudulent and some labeled as legitimate. The training data goes into the system where we train the machine learning algorithm. The algorithm examines the training data, identifies patterns that distinguish fraudulent transactions from non-fraudulent ones, and develops an internal mathematical model based on those patterns. Next, we prepare model input data, the actual features and variables that will be fed into the training algorithms. This might be characteristics of a new transactions, like for example, the amount of the transaction, the type of merchant, the time of day, the location, and so on. This model input data then flows through the machine learning algorithm, which applies what it learned during training to make a prediction about this new transaction. It's likely to be fraudulent. What's the probability? But here's the critical part. When we evaluate the accuracy of that prediction, does the prediction actually match reality? There are two possible outcomes here. If accuracy is unacceptable, then if the system is making too many errors, we go back and retrain the algorithm. Maybe we need more data. Maybe we need to adjust the algorithm parameter. Maybe we need different input variables. If accuracy is acceptable, on the other hand, if the system is making predictions at the level of accuracy that meets our business requirements, then we have developed a successful model and we can deploy it into production. But even after deployment, the process continues. As new data comes in, we continue to feed it through the algorithm. We continue to monitor accuracy, and periodically we retrain with newly accumulated data to ensure the model stays accurate as patterns evolve. So this is totally different from how traditional statistical models work, which is build the model once, validate it once, and then deploy it. Machine learning system, in contrast, is dynamic. It's designed to improve continuously.